Hi everybody, good night. How you all doing? I am going to put my headphones on because I'm going to need that. And I believe we have some people out there already. Okay. So I am on. I'm here. Remember that if anybody wants to Skype, we could try a Skype. I've not done this one before, so we will see how that goes. All right. I wanted to first start off by just sort of going over the exam. All right. I have a Skype call, so let me answer that. I wanted to first. So let's start off with the exam, as I was mentioning. And what I like to do is to just sort of go through each question, and then with each question, we can, just kind of go through the reasoning behind the question to see how we would work the question. All right. Then what I'll do is I will work a question, the question with regression and the question with Anova, because apparently some folks are still having a bit of a challenge with that. So we will go through those two in a bit more detail. But the other ones, I will sort of more or less sketch the formula that we need to use, and then you do have the solution. So we could sort of go through the details of the calculations in that fashion. So let's take a look at this. So back then, what I used to like to do was to create a story, and that story would kind of set the context for the entire exam, and all the questions would be related to that particular context, which some people found was interesting. So this is about a hospital called Sankofa Hospital. And Sankofa Hospital is relatively modern. It's in Dakar. And of course, um, you know, as a hospital that cares about quality and so on, it wants to do a number of studies to assess or to ensure that it's delivering good quality service. Anyway, so it's a fictitious hospital. I made that up, but nonetheless, it gives it context. All right. So we have a number of questions that we need to answer. Let me see. I think that it says here towards the bottom. A graduate of organizational administration from Sheikh Anta Diop University, 12 years of administrative experience. She decided to search strategically for opportunities to maintain the quality of service and the respect of the citizenry that her predecessor had worked so hard to build. She wants to search for cost management opportunities by using analytical tools such as statistics and management science. These tools, she hopes, will help her better understand the systems that are key cost drivers for the hospital. So, story. All right. So here's the first question. First question is that we have Sankofa's labor relations climate has generally been good. There's been no strikes over the last 8 years, even though the nurses and staff are represented by a powerful union, the Working People's Alliance, WPA. With the recent cutbacks, the grumbling in several quarters are starting to become audible. Ms. Candia wanted to find out about the attitudes of Sankofa's employees towards their working conditions. Some 250 employees were surveyed and were asked several questions. On one question in the survey, they were asked to indicate their level of satisfaction with the general working conditions. The results are summarized below. So when you look at this table, we see that we have different categories of employees. So we have nurses, we have support staff, and we have doctors. And then we have the level of satisfaction, satisfactory or unsatisfactory. Right? So they're satisfied with working conditions or not satisfied with the working conditions. So when you look at this table, that should look like what we call cross-tabulation data. All right. In other words, how do we create a cross-tabulation? We create a cross-tabulation by taking two categorical variables. In this case, it is class of employee and level of satisfaction. So these are the two categorical variables. And then we take a big sample and spread out that sample among all the various cells in that table. So in other words, you have a number of nurses who are satisfied, a number of nurses who are unsatisfied, a number of support staff who are satisfied, a number of support staff who are unsatisfied, number of doctors, and so on. So that data, if you look at the values in the table, they are counted. So unlike the data for Anova, where the values are either what we call ratio data or interval data, this data really is actually frequency data. We counted it. All right? And so by looking at the cross-tabulation of the two attributes, we're able to identify a number of nurses who are satisfied and a number of nurses who are unsatisfied and so forth. So this data as frequency data will help us to generate things like proportions. So you're supposed to recognize this table as a contingency table. And then we could, of course, with the data in a contingency table, we could generate proportions very easily. So we're told find a 98% confidence interval for the true proportion of all employees that rate working conditions as unsatisfactory. So we have to pay close attention to what we're being asked. And we're looking at unsatisfactory is what we're interested in. So if you look at under each category, you have a certain number of workers that are unsatisfied. So 35 nurses are unsatisfied, 45 support staff, and so on. But the total number unsatisfied is 110. All right? And the total sample size is 250. So essentially, out of the 250 workers, 110 of them are unsatisfied. Almost half of the workers are unsatisfied. So if you're now asked for a 98% confidence interval for the true proportion, when you see words like true proportion, that should tell you that it's population that we're talking about. Sample proportion is not considered true proportion in the sense that it is an estimate of what the actual value is. Okay? So here we are with this particular question. And so we want a confidence interval for P. But P in this case represents the true proportion of employees who are unsatisfied. So we need to make a note here that that is the proportion of employees unsatisfied, of unsatisfied employees. Okay. Oops. So the sample proportion in P bar would be the 110 over 250. So we could actually figure that out. So in that case, that should be equal to 0.44. So So that's our sample proportion. If we want a confidence interval for the true proportion, in this case we have a single sample, single population, and it's fairly easy to identify that formula because all you got to do is to go look for the row that has P in it, and the formula for the confidence interval is just P bar plus or minus Z, the square root of P bar, 1 minus P bar over N, all right? And that's the formula that we need to use to solve this particular problem. Now, you may recall that there is one condition that needs to be satisfied for us to use the normal approximation to the binomial, because that's what we're doing. We're saying that the sampling distribution of P bar is a normal distribution. Well, P bar times N must be greater than 5, greater than or equal to 5, and 1 minus P bar times N must also be greater than or equal to 5. Since P bar is 44%, you know that 44% of 250 employees is going to be greater than 5. 1 minus P bar would be 56%. 56% is also going to be greater than or equal to 5. So therefore the conditions are met for us to use the normal approximation to the binomial, and that's what we're doing with this case right here. All right. Now, it turns out that the answer to this question, if you look at the solutions, we have a confidence interval, and I'm just going to go to my page where I could see the answer properly. Okay, let's take a look at that, and bear with me. And so we got between 36.8% or 0.368 and 0.512. So for this problem, when we solved it, so it would look something like this: 0.44 plus or minus. And since we have a 98% confidence interval, it will be 2.33, 0.44, and then 1 minus 0.44. So I can make this 4 a little better. Just have to be a little patient, that's all. Over 250. That ends up giving us 0.44 plus or minus 0.072, which then gave us that P lies somewhere between 0.368 and 0.512. As percentages, we could say 36.8% and 51.2%. So that's cool in terms of the calculation, but we do have a question that we want to ask as well. The question says, in the past, 25% of employees felt that the working conditions were unsatisfactory. 25%. Using your response that should not be in B, but that should be in A. Using your response in A, is there sufficient evidence or reason to believe that the proportion of employees who feel the working conditions are unsatisfactory has increased? So if you look at the confidence interval, remember that the answer was 36.8% to 51.2%. So the question is, if you look at any value in that interval, is that value greater than 25%? And the answer is yes. Any value in that confidence interval, that between 36.8 and 51.2, will be larger than 25. Now remember, we don't know exactly what the value of P is. We only have a 98% confidence. level of confidence that is in that interval. And so therefore, we have to conclude that we do have evidence that the proportion has actually increased. We do have evidence because of any value in that interval would be greater than 25%. All right? So since any value in that interval is greater than 25%, we do have sufficient evidence that. So here we go. This was my computation that I did earlier. So any value in that interval here is going to be greater than 25%. So we do have sufficient evidence that the level of employees, or the proportion of employees who are now unsatisfied, has actually increased. Okay? Let's look at part C to this problem. Part C. So Ms. Candia would like to have an allowable error. An allowable error. We could also call that a margin of error. So the allowable error and the margin of error in this case is actually the same thing. So she wants a margin of error of no more than plus or minus 2% for the 98% confidence level. All right? This will require a new study be conducted. It has been estimated that the cost of administering and analyzing each survey response is approximately $3. The cost of preparation time, processing time, etc. Right? That's $3. Ms. Candia has a budget of $5,000. Is it adequate? So you see how, rather than just getting you to calculate the sample size, we want you to do a little more. We want you to go beyond and say, you only have $5,000? What is it going to cost for this new study? So let's figure this out. So remember now that we already have 250 employees, right? Or at least a survey of 250. We need to determine how many more we will need. So the margin of error for our problem, margin of error is 0.02, and that should be equal to Z, which is 2.33 times 0.44 times 0.56 over n. So if we squared both sides and then move the n over to one side and all that sort of stuff, then we'll have the following. So we'll calculate that n is equal to 2.33 squared times 0.44 times 0.56 over 0.02 squared. And that should give us an answer. And I believe that answer is 3345. All right? 3345. 3345. If we round that up. Now, she already has 250, so if we take 3345 minus 250, that is the additional number of surveys that she would need. And then if we multiply that by $3, it will give us the cost of doing this. All right? So if we take 3345 minus 250, that gives us 3095 multiplied by $3 is equal to 9,285. 9,285. So there are two ways to do this. One is to say that you're actually going to do the study completely afresh. In other words, you're going to actually take the total 3,345 surveys, right? But instead of doing that, you could say, no, I'm going to keep the first 250 that I have and then take the additional 3,000, I believe it was, and 45 or something like that, or 95, 3,095. Anyway, either way, what you notice is that the amount of money that you have to spend is going to be greater than the $5,000. All right? So 9285 is greater than $5,000. And so therefore she does not have enough money. Now if you look at 500 divided by 3, and you took that sample size, 5,000 divided by 3 will give us 1667. And then if we added the 250 to that, 250, we already have plus 1667. That is essentially what she can get in terms of a sample size. And using that sample size, we could actually go and figure out what the margin of error would be by simply substituting, instead of where we had 250 for n, we could actually just substitute whatever that sample size is, and will give us an estimate of what the margin of error would be. However, remember, with a new sample size, you will end up getting different data, so the sample proportion would now be different. Okay? And so we have no guarantee of exactly that as a margin of error. So that's that question in terms of how we would approach the issue of, is the budget enough? So after we've calculated the sample size, we now go one step further and multiply that by $3 per instrument or per survey, and then we get what she would need, and it's quite a lot larger than the $5,000 that she has. Okay, let's go to the next question. So we are told here now, if the true proportion of doctors that find working conditions satisfactory is only 50%, what is the probability that in a random sample of 50 doctors, 40% or less would find working conditions satisfactory? But before we do that, I want to make sure that I'm not skipping any questions, because sometimes at the bottom of my page is here we go. I knew it. So here's what we got. Part D. So in examining the data in Table 1, it would appear that the doctors display a significant level of dissatisfaction with working conditions. Generally, they are more vocal and more sensitive to cutbacks and resource shortages. So Ms. Candy was quite surprised, as she had hoped at least 50% of doctors would be satisfied with the working conditions. And that's where we go to that question now. If the true proportion is 50%, right, of doctors who find it unsatisfactory, what is the probability in a random sample of 50 doctors or less would find the working conditions unsatisfactory? So how many, first of all, let's look at the number of doctors that were actually surveyed. If we go back to our initial data. So notice that among the doctors, we have 20% are satisfied. 20 doctors said they were happy or they're satisfied out of a total of 50. That's where we get the sample proportion of 40%. All right. So 20 over 50 gives us 40%. So we're working essentially with a sample size of 50 and a sample proportion of 0.4. So what we want is a probability that P bar is less than 0.4, given that N is equal to 50 and our sample proportion, our population proportion, if we assume that is a 50-50 chance or 50%. So P would be 50%, N would be 50, and then our sample proportion is 40% or less. So this is 0.5, this is 0.4, and we want to find this probability right here. Now you know that Z is equal to P bar, sample statistic, minus population parameter over the standard error. 1 minus P over N. So then if we pull that together over here, we will have 0.4. Z will be equal to 0.4 minus 0.5. 0.5 times 0.5. Notice I am not using P bar because I have P. Whenever you have P, you always use P to calculate the standard error over 50. All right? And once you get that Z value, then you go ahead and you will then do the appropriate computation to find the area under the curve. And so, if I wanted to look at that, let's see what we got. I'm just double checking. It turns out that Z is negative 1.41. And so if we look up negative 1.41 in the Z table, associated with negative 1.41 is 0.0793. 0.0793. So probability of Z being less than or equal to negative 1.41 turns out to be 0.0793 or 7.93%. Now, we could ask you, is that significant? Is that a significant observation, And then it all depends on your value of alpha, your risk of type 1 error. So this is actually a p-value right there. If we wanted to prove or find evidence that the true proportion is less than 50%, that would be our p-value based on this sample. So if we tested the hypothesis at 10%, our p-value would be smaller than 10%. So we would reject the idea that the true proportion is 50% and therefore conclude that there's been a reduction in the number of percentage of doctors who are satisfied. If we decide to use a 5% significance level, then this value, which is our p-value, is greater than alpha. So this would be greater than 5%, so it would not be significant. That is, we would fail to reject HO. However, it is less than 10%, 0.1, so that it will be significant at a 10% level, but not significant at a 5% level. So it all depends on how much risk you're willing to take to commit type 1 error. So how we interpret that probability depends on how much risk we're willing to take. Okay? Let me see if there are any questions at this point. So far, so good. Okay, fantastic. Let's look at the next question. So part E. The data on worker satisfaction is further broken down into 3 levels of satisfaction. Satisfactory, right, indifferent, and poor. So we broke it down a bit more. Take the same 250, but then we said, okay, now rather than looking at it by the class of employees, we're just going to look at, we're looking at the class of employees, but we want to increase the number of levels of satisfaction. So we say some people are actually indifferent, And so if we do the test, then if we spread it out a little bit, we get to see the data a bit better. So here's what we have. The same 2 categorical variables, which is class of or type of employee and level of satisfaction. So now that we've increased it to a 3x3 matrix, we definitely are now looking at a contingency table. All right? And remember, the data in the table represent frequency data. All right? And so we're being told here in this question, or asking this question, is there clear evidence that employee category and the level of satisfaction are related. So sometimes when people see that term, if they have not separated regression from contingency tables, sometimes they try to see if they could actually fit a regression to this. And then say they couldn't figure out which is X, which is Y. So when we talk about two variables being related, linearly related, yes, we're talking about regression. In this case, we're talking about a relationship between two variables, those two categorical variables, where we're dealing with a contingency table, what we call a non-parametric test. So do not confuse those two. Just because we see related, we automatically think of linear regression. We do have two variables can be related in linear regression, but also two categorical variables can be related in contingency tables. So try to avoid that error, okay? And so given that we have contingency tables, then we know that we are talking about a chi-squared test, and we would test the hypotheses that basically the category or the class of employee and the level of satisfaction are independent of each other versus that they're actually related. So classes of employee so class, or we should just say class and satisfaction are independent versus that they are actually related, right? Class and satisfaction are independent versus that they're related. So once you've identified that this is a chi-squared test, things are pretty simple after that. We know that chi-square is the O minus E squared over E. All right? O minus E squared over E. So you have to now calculate the expected frequencies. And to calculate the expected frequency of any cell, so EIJ is the row total for that cell. So that's row I times the column total J over the total sample size, what we call the grand total. All right? So row total times column total over grand total. And that gives us our EIJs, our expected frequencies. And then once you've computed your chi-squared value, then you just need to remember what the you want to get your decision rule. So you know it's a one-tailed test. You know that your degrees of freedom is R minus 1, row minus 1, columns minus 1. And in this case, we have a 3 by 3 matrix, so it would be 2 by 2. So the degrees of freedom would be 4. And depending on what our alpha value is, we can look up the chi-squared table and find our critical value, chi-squared critical. All right? With that, we could then, once we calculate the value of chi-squared, compare it to the critical value, and then we could determine whether or not we should reject the null hypothesis or not. Okay, so for this particular question, I know you have the solutions. I just want to go through the reasoning, how we knew that it was a chi-squared test is because we have a cross-tabulation, or we have what we call cross-tabulation data, where the values in the table are frequencies, the number of observations, which is different from having data in an ANOVA, where the values that look like the values in the matrix are not frequencies. They are values that we measure, like time, money, volume, etc. So that's what helps us determine the difference between the two of them. Okay? For this particular question, I'm just going to see what the outcome was. We got a chi-squared a test statistic of 18.81. So when you calculate all of your expected frequencies and then calculate your chi-squared value, it turns out that chi-square was 18.81, which is fairly large. The critical value for this particular test was, let's see, actually the critical value is 13.277. 13.277. That's 4 degrees of freedom and a 1% significance level. So our chi-squared critical was chi-squared 0.014. If you look that up in the table, it turned out to be 13.277. Well, the 18.81 is larger than that. So using the classical approach, we clearly would reject the null hypothesis. What is our p-value? Our p-value turns out to be less than 0.005. So for those of you who may be having a little difficulty using chi-squared table, it's very similar to the t-table. So let me pull it up and see what I could do here to show that to you. All right, so I'm going to try to pull up the chi-squared table. Bear with me. And we want... because I know that we didn't spend a lot of time on chi-squared because there's not a lot to do there. Once you do one problem, you pretty much have it, and you could run with it. So let's just take a look at the chi-squared table, and okay, here we go. Okay. All right. So chi-squared table is right here. So we have a 1% in the tail, and we have 4 degrees of freedom. So if we take a look at that, we see in the tail 1%, and then the value 13. If you look under the column 0.01, and then you go down to 4 degrees of freedom, you'll see 13.277. And that gives us our critical value, okay, that we have for the test. So that's pretty much it with the calculation, with the hypothesis test. Let's see what else under that question. Okay. I think that's pretty much it under that question. I think we're done now. So our conclusion, we're basically going to reject the null hypothesis, that they're independent, and conclude that employee class or category and level of satisfaction are indeed related. So that's what we're going to conclude from that. Okay. It might make sense to find out who's actually more dissatisfied or more satisfied, but at this point, there is a relationship between them. And of course, the hospital administration should figure out what to do in that situation. Let's go to our next question. Number 2. So the quality of service in the emergency department has been of some concern for a while. Over the past year, patients have had to wait notably longer times for medical treatment. A previous study of waiting times in the emergency room revealed a mean time of 80 minutes and a variance of 100 minutes. Now that was a little trick. The variance, given the variance instead of the standard deviation. And of course, a lot of people missed it. So if you have to calculate a probability, for example, we're told waiting times are normally distributed. So What is the probability that a randomly selected patient entering emergency will wait for at least 90 minutes? So what was the mean waiting time? The mean waiting time was 80 minutes. We want to know that the patient will wait 90. And this is just a single patient, not a number, an average for a number of patients. And so therefore Z is just X minus mu over sigma. Remember we need sigma. Sigma squared is 100, so you got to make sure that you use the right value. So X in this case would be 90 minus 80 over the square root of 100, which is over 10. And that would just be 10 over 10, which is 1.0. All right? And you could figure that out. Now, let's look at part B. So after the campaign, a random sample of 25 patients yielded a mean of 71.12 minutes with a standard deviation of 14.95. So here's our data right here in front of us. And we asked find a 95% confidence interval for waiting time for patients. So in this case, what we're trying to do is to determine whether or not there's been an improvement, whether there's been a reduction. And the way we could do that is by finding a confidence interval and looking to see if, a confidence interval for the true mean based on this new sample data. And then if it turns out that that in that interval, any value in that interval is less than 80 minutes, then we have evidence that there's been an improvement. All right? Because right now it's around 80 minutes and we're actually going to try to find a confidence interval. So when you look at this is a sample of 25. We have a sample standard deviation, and so therefore we're going to use T. When n is less than or equal to 30, we use T, but then not even then, as long as sigma is unknown, we will also use T. So your formula that you have to use is x bar plus or minus T alpha over 2 degrees of freedom S over the square root of n. So with this particular problem, you actually need to go and find the sum of the x's, the sum of the x squareds, and then compute S from that data, compute x bar from that data. Once you have S, x bar, you could figure out what T would be in for 95% confidence level. The degrees of freedom in this case would be n minus 1, which would be 24. So with 24 degrees of freedom, with a 95% confidence interval, the tail is 5%. So 5%, 24 degrees of freedom, we could figure out what the critical value is here for T. We would have calculated the value of the standard deviation, and we have the value of n and the value of x bar. That will give us the information that we need. So let's see what we got for a confidence interval in this case here. (64.95 to 77.29). So that's our confidence interval. So we now have a new confidence interval where the mean, after you do your computation, we get 64.95 minutes to 77.29 minutes, right? And that's in minutes. So, do we have evidence that the mean time has actually decreased? I'm sure you'll agree yes, because any value in that interval is less than 80. Any value. So even if you go to the top value here, 77.29, that is less than 80. 64.95 is also less than 80. So we clearly have evidence that the true mean waiting time has been reduced. Now notice that we've done this as a confidence interval. We could also do this as a hypothesis test. So where HO, we would say that the mean is greater than or equal to 80, HA, that the mean is less than 80. And our test statistic would be T, x bar minus mu, S over the square root of n. That's our test statistic right there. Okay? And so then we would get the value of T, we could look it up in the table, or we would compare it to the critical value which would be T alpha on 2 degrees of freedom. I believe it turned out it was 2.0639 anyway. 2.0639. So as long as we get a value of the test statistic larger than 2.0639, actually in this case, yeah, well, it would be that the critical value would be negative, and so therefore we would need to get a test statistic that is smaller than negative 2.0369. Sorry, 2.0639. And then we would have evidence to support our claim. That's if we're doing it as a hypothesis test. But we could also do this as as I mentioned to you, we could also do this as a confidence interval, which we've just done, but you could get the same result if we use the same significance level and do it as a hypothesis test. Okay? So let's see what our next part of the question is after this one. Probably a sample size problem. So is there clear evidence that the campaign has helped to reduce the mean waiting time? The answer is yes, because any value in that confidence interval is less than 80. So therefore we have the appropriate result. What assumptions are necessary for the interval in B to be valid? So that's something that is important to know. Whenever you're using a t-distribution, one of the assumptions, we have two key assumptions that are important. One is that the population is normal. In other words, the population is normally distributed. We need to make that assumption. So one is a normal population. And two, a randomly chosen sample. So we need to make sure our sample is unbiased and that our population is a normal population. Just that we don't know the standard deviation and we take a small sample size, so we're going to use the t-distribution instead. All right? So that's our assumption that we're going to make right here. We're asked to plot the data using stem and leaf plot. It's fairly simple because all the data basically have maximum of 2 digits, and we need to look at the minimum and the maximum. I believe the minimum value was 42, the maximum was 105. So in that stem and leaf plot, you would simply put 4, 5, 6, 7, 8, 9, 10, and then simply go about recording the values 42, 77, 85, etc., etc. So once you produce the stem and leaf plot, what we wanted you to do with that was to kind of look at the data and see if you see like a bell-shaped curve, all right, from that stem and leaf plot. So is there any reason to believe that the normality assumption is violated? So remember that we said one of the assumptions is that the population is normally distributed. So when you look at the sample data that you have, does it kind of look like a normal distribution? That's what we're asking you. If it was looking something like this, you might say, that assumption that we have there about normal distribution, that is not a reasonable assumption. But if it looks, reasonably symmetrical, then you could say, hey, I think that the assumption of normality is a reasonable assumption. That's what we want you to do here. And of course, when you do the stem and leaf plot, you will get a distribution that kind of looks more like this guy as opposed to this guy. All right? Let me take a look and see if we have any questions, because I have so many files open here that I'm not seeing. I'm not seeing all the questions. So I see we have a couple questions here. All right. Can you write the symbols as well for those? Let me see which one we're talking about here. Let's go back. In terms of chi-squared, I remember I did one on chi-squared, and with chi-squared, it's usually I'll just create a clean page here. With chi-squared, in terms of symbols, HA, we have Pij, which basically means the probability of obtaining a value in row I, column J, is the probability of row I times the probability of column J. Now, the reason why this makes sense when we say that HO is that the two things are independent is because it comes from that probability statement that if you have two events, A and B are independent of each other, their joint probability, PA and B, is equal to the probability of A times the probability of B. So that's like your I and J, and probability of I times probability of J. And then, of course, if they're related, then we don't have this relationship that we get with independence. So Pij is not equal to Pi times Pj. So that's for the chi-squared test. If we were doing the hypothesis one that I talked about a little later on, has there been a change in the mean waiting time, then it would be that the mean is greater than or equal to 80 versus that the mean is less than 80. And that's because we wanted evidence that there was a reduction in the waiting time. If it was that there was a change, then you could say HO, mu is equal to 80 versus HA, mu is not equal to 80 minutes, of course. All right. So that's for the symbols for that. Let's see what other questions we have. The chi-squared formula is not on the formula sheet, as far as I know it is. Bottom, middle, first page. So somebody already answered that. Thank you. So we'll have the formula sheet and tables in the exam. Frankie, yes, we will. Is the final going to be like the one in the story? I think so, Max, but the formulas are different than the ones on MindTap. Are there symbols that we're testing for independence? Are there symbols when we're testing for independence, Hannah? So I just answered that, yes. Is anyone in here really comfortable with Anova? If yes, could we meet at the library tomorrow? Okay, that's cool. I'm going to go over an Anova problem. Also, the decision rules should be based on the p-value or the z-test. Okay, so the questions here, essentially, we would ask you if we want you to do a critical value test or if you're a p-value test. Or what we will do is we will ask you to go through the hypothesis test and then ask you to produce the p-value anyway. So it's important to know both. Don't stop at one, know both of them, all right? So let's continue. I'm going to question 3. So with question 3, Ms. Candia has been informed by the receiving department that delivery lead times the time between placing an order and receiving an order for two of its suppliers are highly erratic. The companies, Geno Limited and Prozac Inc. have both promised the hospital significant improvement in their lead times. A study of shipments received from the two companies over the last 2 years gave us the following information. Now, in this question, I have standard deviation sigma. That standard deviation should be S and not sigma, because if I say sigma, it would determine which model that I would use. Sigma versus S will have an effect on which model. So in this case, when we look at this problem, first of all, look at this information here, mean. So I am talking about a mu. And then I'm interested in a confidence interval for the difference between the mean lead times. So I am interested in mu1 minus mu2. That's my population parameter of interest, mu1 minus mu2. Now, you could do mu2 minus mu1, mu1 minus mu2. It's totally up to you. It all depends on, um, what you're comfortable with. So we want a 90% confidence interval for the difference between the mean lead times. So if you look under on the formula sheet and you look for mu1 minus mu2, there will be 3 of them. So the question is, which one do I use? The very first one is testing for the difference between 2 means for 2 independent samples, but the standard deviations are known. Sigma. So we have sigma 1 and sigma 2. That's the first case. The second case is that we are testing for the difference, or we are interested in the difference between 2 means, but the standard deviations are unknown. The third one, we are interested in the difference between 2 means, but we have matched samples. The samples are matched pairs. Do we have matched pairs here? No. So first thing you gotta do is eliminate this matched pairs situation. So now you have 2 left. One in which sigma is known, the other one in sigma is unknown. Now because I wrote sigma there, if you had chosen the formula that uses Z, then you're correct. But the reality is that data was obtained from 2 samples, one for each of the companies. So that should have been S, in which case you want to use, I believe it is the second row, which has S in it. And then we're going to assume that the population variances are the same. Now remember, your textbook have been just working with the case where the population variances are not the same. In which case, when the population variances are not the same, the degrees of freedom formula is very crazy. But for our case, we work with the simple one. And so it would just be x bar 1 minus x bar 2 plus or minus t into sp squared 1 over n1 plus 1 over n2. Okay? So that's the formula that we would use for that. Of course, you know that to calculate sp squared, you need a calculation that looks something like this. Let's see if I could write it down for you. Where we calculate sp squared and 1 minus 1 times s1 squared and 2 minus 1 times s2 squared over n1 plus n2 minus 2. That is also the degrees of freedom as well. So with that formula, you should be able to actually answer the question. So let us look at the answer to this question. I'm just going to take a look at it to see what we get. And the answer to this question turned out to be 0.57 to 5.23. So the answer was, and the way in which I set up my confidence interval, I use G minus P. Okay, all right. So Geno minus Prozac. So in this case, we have a confidence interval for mu G minus mu P, if we were to use the symbol. So, and we got a value of 0.57, and I believe the other one is 5.23. So you have to interpret that. Is there clear evidence that the firms have different lead time performance? So when you look at this, excuse me, you might be inclined to say, well, the bottom value is just 0.57. It's kind of close, almost 0. That's not the point. If you look at any value in that interval is positive, the interval does not include the 0. And so therefore, if any value in that interval is positive, then mu G is greater than mu P. That's the only way you get a positive result from that difference, is if mu G is greater than mu P. So in which case then we do have evidence that there is a difference between the lead times. All right? And so that difference is somewhere between 0.57 and 5.23 days, I believe it is. If not days, it must be weeks. Let me see the unit. Days. All right? So we're able to interpret that question. We're told one assumption for the interval to be valid is the assumption of equal variances. Now, we did not cover that in the course, so don't worry about this for the exam. But there is a test that we could actually conduct, which is basically an F test. So if we wanted to test the hypothesis that the variances are the same versus that they're different, so it would be that sigma 1 squared is equal to sigma 2 squared versus sigma 1 squared is not equal to sigma 2 squared. That's essentially what the hypotheses would look like. And in our case, what you would do then for your test statistic is that you would take F is equal to, and you have to take the ratio of the two variances, sample variances that is, not population, sample. And for our test, we always put the larger over the smaller. So who has the larger variance? I think it is Prozac. So we will take S squared P over S squared G. And that will give you a test statistic. The degrees of freedom would basically be NP minus 1 would be your numerator freedom, and NG minus 1 would be your denominator freedom. DF1, DF2. Like I said, you don't need to know that for the exam, but I'm just sharing that with you. Actually, this stuff here is quite similar to what we do in Anova with the ratio of two variances. It's just that we call them MS, mean square. Well, it's the same idea right here. So those are two variances. And then we would actually go to the F table, look at the critical value, and do all that same stuff that we do with Anova. But it's not needed for our exam, so we could ignore it. Okay? Let me check, see if there's some questions. Yes, Hannah, that's right. There is so you get that right. Yes, there was a typo in the exam, and back then we did correct it, but of course never bothered to make a correction of that for later production. We have here, Kristen, when we calculate the SP, it says SP squared. So actually, in that formula I just gave you there, that is SP squared. So you don't really need to take the square root of it. If you look here, you will see that that is indeed SP squared. So no point in taking the square root when you only to have to square it back again. All right? Good. So let's see. Okay, and I think Hannah, I've answered your question. So that's great. Let's look at the next question here. We're not going to actually decide, go through the result of this question because, as I said, it's not needed for the exam. Number 4. This kind of question. So what we have here is we're told Geno has made a major attempt to reduce its lead time performance. Prozac, on the other hand, has been experiencing organizational problems and hasn't been able to improve much in the way of lead time performance. Sankofa promises Geno a greater share of his business if it can reduce its lead time to 10 days or less. A recent sample of 15 shipments had the following values. Compute the mean, median, mode, and all that stuff. Easy stuff, but as I mentioned to you, I don't think we're going to spend too much time on that in the final exam. So I'll give you that as one little nugget. Okay? that, but of course you need to know how to calculate the mean. And so for 15 shipments, so therefore, of course, X bar would be the sum of X over N, which would be 87 divided by 15. And then, of course, you could calculate the sample standard deviation, and then use that to calculate a confidence interval and whatever else that we want to do with it. All right? So assume that lead times for Geno, since improving, are normally distributed for mean mu of 10 days and a standard deviation of 2.75. What is the probability of obtaining a mean lead time of 5.8 days or less in a random sample of 15 shipments? So the mean was 5.8 in the sample that we have. So essentially, if you look at this question, I'm really asking you to find a p-value. Okay, so assuming the lead times since improving is normally distributed with a mean of, so what we're going to check is that we believe that the mean, sorry, let's get here, mu is equal to 10, sigma is equal to 2.75. So here we have to note that this standard deviation is sigma. What's the probability of obtaining a mean lead time of 5.8 days or less? All right. So in that case, what we're looking at is the mean is 10, but we now want to look at 5.8 or less. Sorry, wrong. That should be here, 5.8 days or less. So we are interested in P X bar less than 5.8. So again, that's sampling distribution of the sample mean. So your Z value, we're going to use Z, of course, because we have, even though we have 15 shipments, we're given a population standard deviation. So that's where people get tripped up, because they look at this and they say, oh, we got a sample of 15. Oh, that should be T. Small sample. Nope. You have sigma. If you have sigma, it doesn't matter if it's small or large, then you should use Z. So that should be 5.8 minus 10, 2.75 over the square root of 15. And that should give us a Z value. And let me see what I got for Z value. Okay, so it turns out that we have a Z value of negative 5.92. Woo. So for Z value of negative 5.92, you know that the p-value is going to be very small, or the probability is going to be very small. So what this is going to be saying, and it turns out that the answer is less than 0.001 for our table, but I believe that's the smallest area that we have in our table, less than 0.001. But we could actually go down as low as 0.0003, 4 zeros and a 3. We had a different table back then that had more data in it. But we're going to use our table for this test. And so, as you could see, the chances of this happening is very small. And of course, we want you to explain that or to interpret that result. So is there a reason to believe that Sankofa should increase its level of business with Geno? Now, when did it say it will increase the level of business? If it can be shown that it has reduced its the lead times to 10 days or less. So the question is, has it done so? In other words, if you're testing a hypothesis that HO, here's what you'll be testing. You'll be testing HO, mu is greater than or equal to 10, HA, mu is less than 10. That's what we will be testing. And looking at this value of negative 5.92, that's an extreme value. So clearly, the mean cannot be 10. We would have to reject the null hypothesis. And since we reject the null hypothesis, and use any p-value, significance level that you want. If we use 5%, that value that we have there, less than 0.001, is a p-value. It's less than 5%. It's less than 10%. It's less than 1%. So we definitely would be rejecting a null hypothesis. And if we reject this null hypothesis, we will conclude that the mean is less than 10. If we conclude that the mean, we have evidence that the mean is less than 10, then the company should increase its amount of business with Geno because it promised to increase it if it can be shown that the new mean is less than 10. And we do have evidence that it's less than 10. So I'm hoping that you're understanding that. So a lot of that is really interpretation of p-value, interpretation of how you call it, yeah, the problem. Even though I didn't ask you to do a formal hypothesis test, but I wanted you to see that in essence you're doing a hypothesis test. Now, what kind of error might we commit? I haven't spoken about errors at all. Certainly type 1 error. Type 1 error is basically rejecting the null hypothesis when it is true. Now, is there a danger? What kind of danger exists in committing type 1 error here? What kind of danger? So if basically that we reject the null hypothesis when it is true, it means that the company has not reduced its lead time, right? It has not. We believe it has, but it has not. And so what happened is that we will be rewarding a company that is not deserving. The company does not deserve to be rewarded with more business, all right? And so therefore we run that risk of rewarding the company when it does not deserve to be rewarded. And how bad is that? So it means that while we might have seen a fluke right there, then the company will be right back to lead times that are greater than 10, and we're not going to be happy. So in that case, it's important for us to make sure that we minimize the risk of type 1 error. And I think we're reasonably safe because we're looking at less than 1% chance that we are in error, okay? And in fact, I have from a different table, it's actually less than 3 in 100,000. 3 in 100,000. So you know that we're doing fine. All right. So that's that question. Let's keep going. I'm looking for number 5. Let's see if we can figure out what kind of problem this is. So we're told that Sankofa has noticed an increasing trend in the number of sick days taken by its nurses. Many believe that the nurses are under great stress because of dwindling resources. Part-time and float nurses are used to substitute for full-time nurses when staff shortages arise. An incentive program, which has been in effect for 15 months now, is being used to encourage nurses to reduce the number of sick days taken. At the end of the year, the nurses are offered a bonus of 15% of salary equivalent of the number of sick days not taken. So this is an incentive to encourage them not to take their sick days. If you don't take sick days, we're going to give you a portion of that as a bonus, 15% of the value of the sick days not taken. A random sample of 10 employees was selected and the total number of sick days taken before the incentive and after. So notice, before the incentive and after the incentive. So, and then it is this same individual. So employee 1 before and after. Employee 2 before and after. Employee 3 before and after. So what kind of data we have here? We have matched pairs. We have only 2 of them, so matched pairs. And as such, we are interested, we are told, is there sufficient evidence that the incentive has reduced the number of sick days taken? So we didn't tell you, is there a difference between the means? No. We basically asked, has it been reduced? So if you want to express a reduction in the number of sick days, then before should be larger than after. So there should be more sick time taken before. So you could say mu before minus mu after. That then would represent the reduction in the number of sick days taken. So there is a mu d, a mean difference. That difference would represent a reduction, and we would call it mu d. So hence, we'll be looking at mu d, if we want a reduction, then that difference should be positive. So mu d is less than or equal to 0 versus mu d greater than 0. Notice that? Because I am looking for evidence of a reduction. So if I'm looking for evidence of a reduction, then before should be larger than after. And so I can set it up that way. Now, if you actually just put mu A minus mu B, that's okay. It just means you have to change the signs around, the inequalities around, okay? Because then mu after will be smaller, so therefore you'll be looking for mu D to be less than 0. And that's all. And so now you know that your test statistic, remember there were 3 cases where we are interested in the difference between means. One case where 2 cases where the samples are independent, but one sigma is known, the other one sigma is unknown. And then the third one where the samples are dependent. Well, this is the dependent case. So in this case, t is equal to x is equal to d bar minus mu d sd over the square root of n. Okay? And that's the formula that we're looking for. And so we should be pretty cool with that. Let's see if I could just get you what not the decision rule so much, but the test statistic. It turns out that we have when we did our calculations, mu d was 2.2. So I'm just going to make a note here. Not mu d, sorry, d bar, sorry. Wrong term. D bar was 2.2. SD turned out to be 3.46. And when we computed the value of the test statistic, we got t was equal to 2.2 minus 0, 3.46 over the square root of n, which was 15, I believe, or 10 values. All right? And that gave us a value of 2.175. 2.175. And when we computed the p-value, so we decided to do p-value approach, it turns out that the p-value was between 0.025 and less than 0.05. So if we're testing at a 5% significance level, it is significant. If we're testing at a 1% significance level, it's not significant. All right? So that's how we could actually do this. I believe there's a question below there. Let me see if I could. No, let's go to the next page. We're told an alternative experimental design to the one above could have involved randomly selecting 10 employees before and after the incentive program was implemented and conducted a hypothesis test for the difference between the population means, mu B minus mu A. Are there advantages in using the above method versus this approach? So, of course, if we take 2 independent samples, the individuals in the samples are very different. So there could be other reasons. Maybe one sample had a lot of sick people in it. You may have had, one sample may have had a bunch of folks in there that had a lot of overtime, and they decided they wanted to take sick time plus overtime and maybe create a vacation for themselves. So there could be all sorts of reasons why the employee, that you see a difference. So the idea behind using the same employees is to control for variation, control for factors, other factors that could influence the outcome. So in terms of advantages of the current method, instead of actually using 20 people, you only need 10. That's number one. And then also that by using the same individuals, you have basically narrowed down the number of factors that could drive the difference that you observe. And so therefore, if you do observe a difference, there's a pretty good chance that that difference is because of the incentive, not because of some other factors, because you've kept, you've created a control by using the same individuals. All right? Then we have number 6 and number 7, which would be Anova and regression. So those are the two that I wanted to spend a little bit of time going over, since some people seem to be having some difficulty with Anova and regression. So let's spend a little bit of time working those two problems, all right? But before I do that, let me see if there are any more questions. So let's see here what I'm getting for questions, if any. All right, so far, good. All right. Okay. So I'm missing some questions here. So oops. I am looking at so how do we know when to use the F table? First of all, that's not the right question to ask. You need to know what kind of problem it is, and then based on the kind of problem, then you will have a sense of which table to use. So never start with the table, start with the problem. So the first thing is that the problem that you're referring to, Kristen, was a problem that is not going to be on the final exam. So I wouldn't worry about it too much. Okay, so that's the first thing. But then that problem essentially required that we did a test for the difference between two variances. And that test for the difference between two variances happens to be an F test, which is actually the same test that we do in Anova, where the two variances are the mean squared due to treatments and the mean squared due to the errors. Those are actually variances. But in that example that we did there in 3C, it was looking at the difference between the two variances for the two populations in the t-test. We are not required to know that for the final, so don't worry about it, okay? How do we know when to use Anova? Well, you know when to use Anova by recognizing whether it's an Anova problem. Anova requires 3 or more populations. So again, we use Anova when we are interested in the difference between population means for 3 or more populations. So if you notice that a progression has been single population, then 2 populations, right? And so single populations, 2 populations, and then 3 or more populations. When we get to 3 or more populations, then now we are moving to Anova. But that 3 or more populations have to do with being interested in the difference between the means. All right, so that's how you know when to use Anova. And it is very important that you recognize that the data has to be data that is interval data or ratio data. The data has to be measured as opposed to counted data. So we tend to use counted data or frequency data in contingency tables, but measured data in we use measured data for Anova. All right. Thank you, Max. Max, you seem to be right on top of things. That's good. I like that. So, but in question 3, we are not comparing 3 or more groups. So, Kristen, as we've already mentioned, question 3 it was not an Anova question, but it required an F test for comparing 2 variances. All right. But we're not required to know that particular test for the exam, so just don't worry about that part. All right. Now let's move to question number 5, or 6 actually. So question number 6. We have one of the studies recently conducted at Sankofa was focused on identifying key cost drivers in various aspects of the hospital's operations. It was noted that at the level of the wards, monthly expenditures seem to be related to the daily average number of beds occupied for the corresponding month. The following data for the intensive care ward over an 8-month period was observed. So we had daily average number of beds. And then the expenses are in thousands of dollars. So if we look at the data that we have, let's go to the question number 6. You have the sum of expenses squared, the sum of daily average number of beds, daily average number of beds squared, and daily average number of beds times expenses. So how would you know what kind of problem this is? So let's look at it. So we are given the following data. We are told to compute and give an interpretation for the coefficient of determination. So which model has coefficient of determination? Well, there's only regression. So in that case, that identifies the kind of problem for us very, very quickly. And then we could see that there seemed to be some kind of relationship between the daily average number of beds and your expenses. All right? So one of the things that we need to know is which is the dependent variable and which is the independent variable. So the daily average number of beds used is going to influence the expenses. So the more beds you use, the more you incur expenses. The less beds, less expenses. All right? So in that case, for this particular problem, we would use the expenses as Y. Sorry. Now, some people have this tendency to believe just because the expenses was first, then must be the X. No, we deliberately mix it up. So that way you have to know the relationship between what's dependent and what's independent. So this is now X over here, X squared. And then this is X times Y. And we can't give you Y times X, it's the same thing. So we want to find the coefficient of determination, R squared. So let's just kind of figure out. So if we want R squared, that's right in our formula sheet. So we could actually get that very easily. So that we could actually get R squared as SSXY squared over SSY times SSX. Now you're not going to see that formula. What you're going to see is R is equal to SSXY over the square root of SSX times SSY. Sorry, I have them reversed over here. It's not a big deal, but let's just be consistent. X, and that's Y. So to get R squared, if you square both sides, you will get, this term right here. All right, you get rid of the square root sign, and then you have to square the numerator. So that's essentially what it is. So it means that for this question, we need to go and calculate SSX, SSY, SSXY, SSE. So right at the top, calculate everything that you think you might need. SE. What else? We have R already. So if we could calculate all of these things. Oh, and the SSR. So if you have SSR, SSE, SE, then we're good to go. All right? So what happened in this question is you're given some partial values, which are the sum of the x's, sum of the y's, some of the x squared, some of the xy's, and all that sort of stuff. So given that we're given that information, we could actually go ahead and compute those various things. So let's do that, okay? So just to make life easy for us, instead of using DA and B and expenses, once we know that X is DA and B and Y is expenses, then we could go ahead and do this, all right? So our sum of X, it turns out to be 144. sum of y, sorry, let's do a sum of x squareds. Sum of x squareds is 2868. All right. Sum of y would be the expenses, so that's 280. Sum of y squared would be 10906. And then sum of xy would be 5569. 5569. Okay, so that's given to us. So now let's find a number of these terms right at the top. SSX. So SSX is just 2868 minus 144 squared over 8. And that turns out to be 276. SSY, so y squared 10906 minus 280 squared over 8, and therefore that gives us 1106. SSXY is equal to 5569 minus 280 times 144. 144 times 280 over 8, and that should give us SSXY 529. All right. So now we have all of these values. Let's continue because we have a couple more that we need. That we will need. So we already know what SSY is. Let's find SSR. SSR is SSXY squared over SSX. So that is 529 squared over 276. And that turns out to be 1013.92. 1013.92. The next value is that we need is SSE. Now SSE, you may recall, is SSY minus SSR. And that simply comes from the formula that SSY is equal to SSR plus SSE. So that is just simply 1106 minus 1013.92. And that gives us 90.08. No, 92.08, sorry. So that gives us SE. SSE. The other thing that we know is that if we want the standard error, SE, which we will need later on, SE is the square root of SSE over n minus 2. But what is SSE? 92.08 over 8 minus 2, which is 6. And if we take the square root of that, we will get ourselves an SE of 3.92. Excellent. So I think we're doing pretty good. So now let's go to so we have all this data that we've calculated up front. If we do all of that up front, the rest of these questions, this particular question is just a matter of plugging in numbers and interpreting, of course, the results. So let's go back and see what they want us to find. So we wanted the coefficient of determination, which is r squared. So let's actually go and find r squared. That I will put down. But we could also express r squared as SSR over SSY. So let's look at that. Actually, let's go back here and put that in here. Let's use a different color. So r squared turns out to be SSXY squared over SSX times SSY. So if we do this, also too, let me just mention that this is also the ratio of the sum of squares due to regression over the total sum of squares, SSY. SSY is the same as SST, in case you're wondering. All right, SSY and SST are the same. So that's another way to express it, as a ratio. All right. So if we do the substitutions for these values, SSXY squared is 529 squared over SSX, which is 276, times SSY, which is 1106. Turns out that we get an r squared of 0.9167. We could express r squared as a percentage, which is 91.67%. Why? Because r squared explains for us the percentage of the variation in the values of y that is explained by the regression line. So in this case, almost 92% of the variation in the values for expenses can be explained by the regression line. So about 92% of the variation, variation in the expenses can be explained this is by the regression. Okay? That's pretty high. So therefore, this regression line is a pretty good line. I could tell you that up front. Okay? So this regression line is actually a pretty good line. So that's r squared. And if we want r, all we have to do is to take the square root of r squared, and we'll get r. Let's actually find it. Why not? Doesn't hurt. Whether or not we ask for it or not, but we could certainly look at what r is equal to. So in this case, r is the square root of r squared. I'm sure you'll agree with that. Square root of 0.9167, and I found a value of r of 0.957, 0.957. So remember that r varies between -1 and +1. Well, this is very close to +1. Because the slope is positive, it means that, because r is positive, the slope is positive. All right? And so you have a very, very high correlation coefficient, which is this, but this is the coefficient of determination. Coefficient of determination. All right? So that's the first question that we were asked. Let's see what's the second question. Fit a least squares regression line for the data. Let's see what else is there. And what does the slope and the intercept mean? All right, so let's do that. And then we want a 90% prediction interval for the total expenses for a month with a daily average number of beds, 24. So fit the least squares regression line. That's the first one we're going to do. Least squares. So the least squares regression line, you may recall, it looks something like this. Y hat is equal to B0 plus B1x. But if we wanted to use the names involved in the actual question itself, then we should call it expenses hat, which is basically prediction of the expenses, is B0 plus B1 times the daily average number of beds. We know B1 is SSXY over SSX. Excuse me. Goes SSXY again. 529. SSX. 276. And that gives us a value of 1.917. B0 is the sum of y over n, which is y bar, minus b1 times the sum of x over n, which is x bar. That turns out to be, what is this, y? 280 over 8 minus 1.917 times 144 over 8. This turns out to be 0.5. And so therefore our equation looks like this. Expenses, predicted expenses, is 0.5 plus 1.917 times the daily average number of beds. That's the regression equation. So how do we interpret those? Well, let's start off with B0, the intercept. So the interpretation of the intercept would be the value of the expenses when the number of beds would be 0. The daily average number of beds is 0. So you could actually, and in that case, that B0 is really $500, right? So you might conclude that when there are no beds occupied, that it will cost you $500 to run the ward. So it's kind of like a base cost. So that might be paying for the lights, the water, whatever else, the air conditioning, etc. $500 for the month for this ward when none of the beds are occupied. What does the slope mean? Well, the slope is rise over run. So for every increase in the daily average number of beds, for every unit increase in that, we will have an increase in expenses of $1,917. Remember, our answer was in thousands. I mean, our expenses was in the thousands. So in that case, each additional bed, once it gets occupied, will increase the costs for the ward by almost $2,000. So basically, a bed per night costs $1,917. So imagine if you had to actually recoup the cost of that yourself. Ooh, a hotel room, I mean, you're talking about a 6-star hotel room for $2,000 a night. All right? The kind of prices that major movie stars pay. So it's quite expensive to run hospitals, as you can see. So that's what the slope would mean. Each bed will cost you $1,917, each additional bed. And that's the interpretation of that. Okay? I believe the next thing we had was to get a prediction interval. Let's double check it. Yes, find a 90% prediction interval for the total expenses for a month. So a couple of things to note in that question. One, we're looking for a prediction interval. The other thing is that we're not looking for an average. So we want a month with a daily average number of beds of 24. So we're saying that for cases when you have the daily average number of beds is 24, there's a distribution of expenses. In other words, a number of possible expenses. We're not trying to predict the average. We want to predict what the actual expense will be. So give us a confidence interval, even though we're referring to it as a prediction interval, it's a confidence interval for the actual expenses for a ward that had a daily average number of beds of 24 for a given month. All right? So what is the formula that we would use? Remember, in regression, we have two formulas. One to estimate the averaged expenses, and the second one is to estimate an actual value. So an average value of y, the average value of y at a given x versus a predicted value of y at a given x. And so we want a prediction interval, and as such, our formula should be as follows. It should be this formula right here. Y hat plus or minus t SE. So you see now why we calculated SE earlier, because we're going to need it. And since we want a prediction interval, 1 plus 1 over n plus xp or xg given to us minus x bar squared over SSX. So we have everything except for x bar, but remember x bar is just the sum of x over n, which turns out to be 144 over 8. And we could figure out what that is. So you could plug the numbers in here, and what happened is that we get, so we're trying to predict expenses. We believe that the expenses, when you have an average number of beds, would be in the following region, somewhere in this following region right here. I think the answer that we got was between 36.98 and 56.02. 56.02. Now, because our answers our expenses are in thousands, we really should be saying 36980 56020. All right? So in other words, what we're looking at is that the actual expenses when you have 24 beds occupied will be somewhere between $37,000 and $56,000. Huge costs in running that situation right there. Now, this particular question didn't have hypothesis test for correlation. It didn't have hypothesis test for the slope. So let me just kind of show you what we would have done if we actually did have those questions. So a question involving the correlation coefficient, we would ask you something like, at alpha is equal to 5% or 10%, whatever, or 1%, 2%, anything. Is there evidence that the daily average number of beds and expenses are linearly related? Is there sufficient evidence that they're linearly related? So in which case, we'll be testing HO, HA, rho is 0 versus rho is non-zero. If they're not related, then rho is 0. If they are related, rho is non-zero. And the test statistic for that is R minus rho over 1 minus R squared over n minus 2. We've already calculated R, which we said was 0.957 minus 0 over 1 minus 0.917, I think it is, or 6. 0.916, where is it? 9167 over 8 minus 2. And then from that, we could actually compute a t-value. I will leave that for you to compute that, all right? And then if we gave you an alpha value, you just need to convert that alpha value to a critical value and compare them. Or you take that t value and find the p value. Remember, this is a two-tailed test. And so therefore, whatever area in one tail you get, you're going to have to double it to give you a p-value and then compare it to alpha, okay? And then you'll be able to do the test. So that test is a test for correlation, and it should read something like, is there sufficient evidence, right, that number of beds and expenses are linearly related? The last one, which is, what if you would then ask, does the daily average number of beds help to explain expenses? Does the daily average number of beds help to explain expenses? So if you look at the formula, expenses is equal to beta 0, plus beta 1 daily average number of beds. Oops. Let's make this a little neater. So it would be expenses, beta 0 plus beta 1 daily average number of beds. So the idea is that if daily average number of beds doesn't tell us anything about expenses, then the slope beta 1, or that coefficient, should be 0. So that way it removes daily average number of beds from the equation. But as long as beta 1 is non-zero, the daily average number of beds will influence your expenses because it's in the equation. All right? So the hypothesis test we'll be conducting is HO, beta 1 is equal to 0 versus beta 1 is non-zero. And all you need to know is that the test statistic is B1 over SE divided by the square root of SSX. Now I could put B1 minus beta 1, but we know beta 1 is 0 from here. So we could just drop the beta 1. Doesn't matter. All right? For this problem, you will get exactly the same answer as up here. But remember, we've already calculated SE, we already have SSX, and we already know B1. So therefore, we could easily compute this value. So your T would be, in this case, B1 was 1.917 minus 0. SE we found was 3 point something. Let's see, what is SE? 3.92 divided by the square root of SSX. SSX was 276. Okay. And that certainly should do it for us. So we should get a t value right there and then figure out what that is. Okay. Actually, let me just compute it just to see what it looks like. So we would have square root of 276 equal multiplied by 1.917 divided by 3.97. The test statistic on that is 8.02. Have you ever seen a test statistic this large? So you know we will be rejecting the null hypothesis and that beta 1 is indeed non-zero, right? So I think that that covers regression pretty much, folks. If you could just identify that we have two variables, X and Y, one is dependent on the other, and that we could then, and then remember too, that data is a data that you have to be able to calculate the mean, and we calculate the standard deviation. So it's not like proportion data. So when you look at the values, you are measuring, these variables are measured, all right? We're measuring the amount of money spent. We're measuring the amount of beds. We could say, yeah, we're counting beds. Yes, that's right. But we're looking at the daily average number of beds. So it's different. We're measuring the average number of beds, not counting the average number of beds, but we're measuring the average number of beds. So that is a regression question. Last but not least, let's do that correlation problem. But before I go on, let me see if we have anybody with questions. No, so far, no questions, and some people, oh, there are questions. I just did not. Okay, so question from Kristen. Okay, first of all, it's okay. I'm sorry. What is the difference between one-way ANOVA and two-way ANOVA? Okay, I'm coming to that. We're about to talk about ANOVA. Two-way ANOVA has blocks included. Thank you, Hannah. Where on the formula sheet does it say that SSE is equal to SSY minus SSR? And Chris Bluto says last page, top right corner. So remember SSR for regression, SSY for regression is the same as SST. So when we say sum of squares total in regression, we are in fact talking about SSY. All right? And SSR is the sum of squares due to regression, and then SSE is the sum of squares due to the error. Okay, so Han, I think you see it. Thanks, no problem. And that's all right with the smiley faces, that's okay. Chris Bluetooth, general question. How many decimals do you want us to round to keep in intermediate? I would say 2 to 3 decimal places would be fine, right? I don't think we need 4, unless we're talking about proportion. If the question is proportion, consider 4. If the question is just just some other variable, 2 decimal places will be fine. Okay. So, Hannah, let me see. F statistic for ANOVA, like, is the F value we calculate in the table or our test statistic. F statistic. So the F statistic for ANOVA, well, whenever we do ANOVA, we have a critical value and then we have a statistic. The statistic comes from your calculations, but the critical value comes from your table. Always remember that critical value is just a limit or boundary for you that comes from your table. The actual value that you calculate is what would be a test statistic. So now let's work that very last problem. Let me see. When do we use the other estimation? So folks, like questions like that, when do we use the other one? If you check the textbook, the ebook, it will actually tell you, it will give you both formulas and will give you the conditions under which you use each formula. I think that part of the challenge with some of the questions that I'm reading is that a lot of these answers are actually in your book, but it all depends on whether or not you choose to read the book. So the book would have given you a confidence interval for the mean value of y at a given x. It will also give you a prediction interval for an actual value of y at a given x. And I'm pretty sure that the book will tell you the difference between the two. So that is the answer to when to use the other one. All right? So at some point in time, you need to go and read through the preamble or the narrative around the formulas in the text. You cannot expect to do an entire course without looking at the textbook. So you have to use that as a resource. Now, MindTap already has the readings right there, which I've pulled out the parts that we are interested in. So if you go under the regression chapter in MindTap, you will see both of those formulas and will tell you when to use them. One for the expected value of y at a given x, and the other one for an actual value of y at a given x. So that the answers are there. All right, cool. So let us do Anova, the last question. So if we look at, and rest assured that in most exams, we wouldn't give you a one-way ANOVA and a two-way ANOVA. There's usually one or the other. If we don't know which one, it could be either one. It all depends, all right? So let us look at the Anova question. So here we go. Going to switch screen here. So Miss Candia wanted to find out how patients of the hospital felt about the quality of service they received. She commissioned a survey of patients upon leaving 3 wards: geriatric ward, recovery, and intensive care. The sum total of the scores for the 3 criteria, comfort, assurance, and courtesy, are given below for randomly selected patients from each of the 3 wards. Each criteria is rated on a scale of 1 equal to poor, 5 excellent. The aggregate scores is formed by adding the score for each patient, right? So basically what is that, a patient who gave a 7, that 7 came from adding up the scores from 3 criteria. So in other words, if the person gave a 5 for all 3, they should have been 15. If they gave a 1 for all 3, it should have been 1. So the scores will vary between, 1 for all 3, the score would have been 3. So the scores will vary between 3 and 15, right? So at a 10% significance level, is there significant evidence of a difference between the mean? So that's how you know with ANOVA versus things like chi-square. An ANOVA question will ask you for a difference between the means of the treatments or the means of the blocks. We're talking about means. So that here, ANOVA always have to do with means, not proportions, but means. All right? In that case right there. In regression, of course, it's a different application of ANOVA. But when we're talking about one-way ANOVA and two-way ANOVA, we're talking about 3 or more populations, and we are interested in the difference between the means. So the population parameter of interest would be mu1, mu2, mu3, mu4, etc. All right? So, question, is this a one-way ANOVA or two-way ANOVA? Now we look and we see we have same sample sizes. So sometimes people might think, oh, that's a two-way ANOVA. But remember that we have geriatric patients, patients from recovery, and intensive care. So in this case, we had actually I think it is what, 1, 2, 3, 4, 5, 6, 7, 8 patients in each category. Those 24 patients are independent of each other. So the sample for geriatrics is independent from the sample for recovery and so on. Okay? So I'm just looking to see here. So you can see here the sum total of the scores for 3 criteria are given below for randomly selected patients from each of the 3 wards. So patients from each of the 3 wards, that's 1, that's 1, that's 1. So these are 3 independent samples. So in terms of the hypotheses, what we're going to be saying is that mu1 is equal to mu2 is equal to mu3, or at least one is different. Okay? At least one of them is different. And the test statistic is it's a one-way ANOVA. So why is it one-way ANOVA? It's completely randomized design because the 3 samples are independent. So it's MSTR over MSE. That's the test statistic. Cool? So we have to go ahead and try to find MSTR. How do we find it? So a couple of things to keep in mind to find MSTR. First thing we need to know is that there is this notion that SST, total sum of squares. So the way in which we do ANOVA is that we're analyzing variance. Of course, that's what the term suggests, analysis of variance, is that we want to look at the variance across the treatments and compare that to the variance within the treatments and see which one is larger. And then, of course, if there's a difference between the means, then the variance across treatments should be much larger than the variance within the treatments. All right? So what we're doing is we're saying that when we look at all these 24 values, there's a total sum of squares, total variation. But it's made up of two parts. If we look at it group by group, there's variation across the groups. And then what we cannot explain, we will just call it SSE. That's what's left. All right? So how will we find SST? SST, the sum of squares total, is just basically taking all your xij's, squaring them, sum of xij, all squared over n. So it's just as if we were finding standard deviation or variance, but for all of the values at the same time. Then we will calculate SSE, which is the sum of squares, but that is within the groups, for each of these groups separately. So it's like repeating what we just did here, but we're doing it for each sample separately. So you could find the SS associated with geriatrics, plus the sum of squares associated with recovery, plus the sum of squares associated with intensive care. That's the three of them that will give you the SSE. All right? How do we find that? So for example, SS of geriatrics is just the sum of the xij's squared, sum of xij, all squared. But then that is, instead of, notice now I'm using NJ, which is the sample size for that particular sample. So for geriatrics, I call it J, but I probably might want to use G for geriatrics. Then I do the same thing, SSR for recovery, and I take the sum of xij squared, xij all squared over n. So if I use, let me just use G for geriatrics over here, R for recovery over here, and then I repeat the same thing. SSI, sum of xij squared, xij all squared over n of intensive care. But notice that the values that we're going to use here are just the values in the sample for intensive care. The values over here are just the values for recovery, and the values over here are just the values for geriatrics. So each of these samples are treated independently, and we find the sum of squares for them. So once we have the total sum of squares for all of the data as one big block, and then you have the sum of squares for the three individual blocks, then you could find SSTR by subtracting SSE from SST. That's all we need to do to find what we need, all right? So SSTR for treatments is SST minus SSE, all right? Okay, so how should we set up this problem so we make our life relatively easy? You know that you're going to need a sum of squares and so forth, sum of x's and sum of all. So one of the ways in which I've done it with my class is that I have done the following. So I'm going to look at geriatrics, I'm going to look at recovery, I'm going to look at intensive care. And we have 7, 10, 12, dot, dot, dot. The last one is 9. Then we have 6, 5, 7, dot, dot, dot. The last one is 10. Then we have 6, 4, 4, dot, dot, dot. The last one is 7. So what I did was basically, I know that my sample size in all of these would be 8. So I have n is equal to 8, 8, 8. I have the sum of the x's, and then I have 67, 68, 53. Then I take the sum of the x squareds, and then I get 599, 628, and 375. Okay? So what am I going to use that for? I'm going to use that to find the SS values for each of these samples. But remember, I also want SST total for all of the data. So 3 8's 24. If I add up all of these values over here, I will get 16, some of the x's, I will get 188 and 1602 for the sum of the x squareds, right? So now, doing this, I could actually calculate my SS values. So now I could calculate and put it in a different color, SS. And the SS values, you know how to do that from trying to calculate standard deviation. So rather than trying to do this all over again, I think I'll take for granted that you know how to calculate SS. So 37.875 for this one. For the next one, SR is 50. And the third one is 23.875. And then for SST, it is 129. All right. So when I add up these three, I will get SSE, and this here is SST. So now I have SST and I have SSE. I could find SSTR. So SSE turns out to be, let me find the value of SSE. 111.75. 111.75. Okay. So that's pretty much, that's the calculations there. So as you can see, with one-way ANOVA, it's really not that complicated if you use this approach. If you just follow the formulas that the textbook gives you, the textbook gives you this formula for total. I mean, it gives you the formula that you would use for the total. But then if you then try to use the formula for SSTR, it's cumbersome. Formula for SSTR, you have to use NJ x bar j minus x double bar squared. That's what you're going to use. So that means you have to go and find the mean for each of them, the grand mean, and then do this. Yeah, you'll get the answer. But the approach that I've just mentioned is a lot easier to do, right? Because why? Because we're already familiar with using that technique for calculating standard deviation, which is sum of x squared, sum of x all squared over n. We're already used to that. And so that makes our life a lot easier if we use that approach. So we need SSTR, which we know is SST minus SSE, which basically would mean 129.33 minus 111.75 is equal to, and is equal to 17.58. 17.58. So that is your SSTR, 17.58. Once you have that, then the next step for us is to simply go ahead and create our summary table. All right. Now, if you look at the solution I gave you, it didn't have the summary table like I do now. This is a lot better to have the summary table. So we need sources of variation. We need sum of squares. We need degrees of freedom. We need the mean square, which is really the variance. We need our F statistic. And we could find an F critical. We could find a p-value. So sources of variation, treatments, error, total. So the treatments we said was 17.58. Error we said was 111.75 and 129.33. Degrees of freedom we know is k minus 1, so there are 3. So there will be 3 samples, three populations. So 3 minus 1 is 2. N minus k for the errors. So we have 24 minus 3 is 21. And then when we add 21 and 2 give us 23, which is n minus 1. Now to find the mean square, a mean square is just a sum of square over the degrees of freedom. So for example, mean square due to treatments would be 17.58 over 2, right? So when we do this, we have 8.79, 5.32, and then we know that the F statistic is a ratio of MSTR for treatments over MSE. Well, our MSE is this guy right here, MSE. Our MSTR, so all we got to do is take the ratio of those two to get our value. It turns out that the ratio of those two gives us 1.65. Okay, so what is our critical value? Our critical value for this problem F critical, if we're testing at 5%, is F.05 to 21. And so we got to look up that. We got to look that up in the. We got to look that up in the F table. Let me just find that value. We're almost done, folks. Been a long night. The critical value turns out to be, I believe it's 3.47. Let me see here. If I use a 5% significance level, so let me just find it properly here. 5% significance level. And we want F distribution. So we're looking for 221. 221. 2 degrees of freedom numerator, 21 degrees of freedom denominator. So if we're doing a 10% significance level, it would be 2.57. But if we're doing a 5% significance level, it would be 3.47. So this is 3.47. In the solutions there, I have a mixture. I have 10% and then I have 1% and 10% and 5%, but we'll just do it at 5%, 3.47. So that's our critical value, 3.47. So let's look at the p-value. Since we're already there, we're trying to find 1.65. Well, 1.65 doesn't exist in our table. So what is very clear is that to get to 1.65, the area in the tail has to be greater than 10%. So the p-value is greater than 10%. And then we're done. So given that we have this information that you see here, you could see that we will not reject the null hypothesis because our test statistic is actually smaller than our critical value, and then our p-value is greater than alpha. This is greater than 0.05. So we will fail to reject the null hypothesis. So in this case, question is that, is there a difference between the mean ratings for the different patients? No. We have insufficient evidence of a difference between these patients. So let's see what we were testing again. Question: is there evidence of a difference between the mean rating of the hospital serviced by the three groups of patients? We have insufficient evidence of a difference. So they're pretty much all rating it the same, is what the data seem to suggest for us. All right. We have our decision rule. And let's see what else is left in that question. I think we have the conclusion. And I think that's pretty much it. So given that since the p-value is greater than 5%, we will fail to reject HL. In which case, we have insufficient evidence of a difference between the mean. Insufficient evidence of a difference between the mean ratings. All right? Very bad handwriting, I know that. Anyway, so we have insufficient evidence of a difference between the mean ratings. And that does it. So if we had two-way ANOVA, what would we have to do differently if we had two-way ANOVA? Well, if we had two-way ANOVA, remember that we said that SST is equal to SSTR plus SSE. We have to break down SSE now into SSBL, and the balance we will still call it XSSE, which basically means what we cannot explain. Unexplainable, but this is now due to the blocks. And now we use a different formula where the SSTR for treatments would be the size of the blocks times x bar j minus x double bar squared, and then SSBL would be k, which is basically the number of treatments, times x bar I minus x double bar squared, and then that gives us SSTR. SST is calculated in exactly the same way we calculated it before. And so now that we have SST, SSTR, and SSBL, we could calculate SSE, which is what's left. All right? And so to do the calculations, once you calculate your X, what you would have to do for each of them is calculate your means. Each column, calculate your mean. Each row, calculate your means. Then calculate the grand mean for all of the data. That's what X double bar is the grand mean, Xij over N. The grand mean for all of the data. Once you have that, then just simply plug into the formula. All right? B times X bar 1 minus X double bar squared plus B times X bar 2, right? Minus X double bar squared plus B X bar 3 minus X double bar squared. That will give you your SSTR. Then the other one will be K times X bar 1. In this case, we have, depending on how many rows you have, or blocks, X bar 1 minus X double bar squared plus k times x bar 2 minus x double bar plus however many blocks that we have, all right? Cool. So there you go. Once you've done that, then the next step is to create your sources of variation. SOV, SS, so you have your SSTR, SSBL, SSE, all add up to SST. So those we know how to calculate. The other thing is our degrees of freedom. We must keep that in mind. The degrees of freedom is k minus 1, b minus 1, and this is k minus 1 times b minus 1. And then down here is n minus 1. All right? So, and then of course we know to calculate our mean square is just SS over DF will give us our mean square. And then we have two F values, an F due to blocks and F due to treatments. So when we take MSTR over MSE, we get an F value due to treatments, and MSBL over MSE, we get an F value due to blocks. And you may ask the question, are we ever concerned or interested in the situation where we are looking at blocks? Yes, in some cases we are. And then, so in some cases we are interested in whether or not the block means are different, but most cases we are interested in the treatment means. All right, that is usually set up to identify a difference between the means of the treatments, not so much the blocks. But in some special cases, we might be interested in the blocks. All right, so that gives us two-way ANOVA in a nutshell. And the important thing to note, because I said to you, we won't give you to do every single piece of calculation, is really what the formulas are, how to pick the right model. And remember what two-way ANOVA is. Two-way ANOVA, or what is called randomized block design, is really an extension of that match pairs test. Remember match pairs, we had two populations, but they were repeated or they were matched. Now we have three or more. So when we expand that to three or more, that's when you get two-way ANOVA. When it is two independent samples and you expand it to three or more, you get one-way ANOVA, all right? Or what we call completely randomized block design. Completely randomized design, my apologies. But in terms of three or more match samples, then it is completely randomized block design, okay? And that's the difference. The last thing that I want you to think about is the significance of the errors whenever we get into a type 1 or a type 2 error. Always ask yourself, what is the cost or what is the implication of a particular error? So for example, if in this case we reject the null hypothesis, that means that we conclude that there's a difference between the patients, how the patients see the service, right? As opposed to that there's no difference. So so if we reject the null hypothesis, then we could commit type 1 error. What is type 1 error? Type 1 error is rejecting the null hypothesis when it is true. So what is bad? What can be bad about concluding that there is a difference between the means when there's no difference? Well, perhaps what can be bad is that we might believe that some people are happy and we don't need to concentrate on everybody, but just figure out who's the unhappiest and then deal with their concerns. The others will, of course, will get upset as a result of that. So it makes one or more of the groups as opposed to all of the groups. So that's basically what the implication of the error would be. Now, if we had failed to reject the null hypothesis, let's assume we failed to reject the null hypothesis, which is the possibility of type 2 error. So type 2 error is failing to reject the null when it is false. So the null is false, but we did not. There is a difference between the patients, but that's not what we concluded. There is a difference between them. So what happens now is that the implications of that could be, if we believe that they all have the same view of our service, then we may want to try to implement measures to address all of them, all of the different customer segments or the groups. We may want to do things or take on activities for all of them, whereas maybe it might just be one group that is not satisfied who requires some attention. All right? So in that case, you might end up spending more money or more effort, time, and energy in trying to improve customer service when in fact you only needed to focus on one group. So if you fail to reject the null when it is false, you are in essence treating it as if all the patient groups have the same view of service when in fact they do not. All right? And it might cause you to want to make improvements for everybody when perhaps you only needed to make some improvements for one group. So that kind of logic is very important because it shows that you now understand statistics at a deeper level where you can now apply it to make decisions. All right? So I think that we're almost at 11 o'clock, and I said that I was going to actually break up the periods. It just so happens tonight that things changed by the time we came around to the session. And so we sort of kind of like are wrapping up things right now. So I'm assuming, I'm hoping that this was useful. I think we've gone on pretty long. And we have some diehards who are still with us. And yes, there is, when this video gets processed, it's pretty long. It would be nice to be able to cut it up. But I will be posting the link to the Facebook group and sending people the link as well. I may see if I might be able to cut it up a little bit before I post it. Well, it gets posted automatically anyway. But what I might try to do is to see if I could download it and chop it up into smaller pieces, because I'm pretty sure we are here from 8 o'clock. So we're getting to 3 hours, and it's hard to watch a 3-hour video. So I'm going to try to see how I could break that up. Okay? So folks, on that note, I've gone way past the hour and a half that I thought we would need. And I'm hoping that you understand how to. If you understand what we went through tonight, I think you'll be in good shape. All right? And in terms of a strategy, well, I always tell people, don't ignore the textbook and learn the language. Review the glossary of terms so that you know the language a bit better. When you do your exam, read the entire exam before you start to work. A lot of people like to rush straight ahead, but read the entire exam. Highlight the ones that you know you can do very well. Do those first, because when you do them first, they motivate you, they encourage you, they excite you. And then you go after the ones with a bit of confidence. You go after the ones that you are less confident about, but with more confidence. If you try a problem, the very first problem you try, you got difficulty with it, it shatters your confidence. And that is carried through to the entire exam. So trust me, it is not a good idea to start from question 1. Read the entire exam and then do the easy ones first and then go after the tough ones. All right? And then make sure you go over the exam again. I want to see everybody do well in that exam because I believe it's possible. All right, so having said that, if there are any last minute questions or anything, I will keep monitoring the Facebook page if you guys want to post some questions there. So that way either another peer might answer it or I'll come and answer it. That would be great. Okay? So on that note, good night, folks, and thank you for joining the tutorial or the session. And best of luck with the exam on Saturday. Take care. Bye-bye.